there was a question about the quiz, so I just wanted to let everyone know. The quiz is going to be true, false statements or multiple choice type of questions. And you can attempt the quiz the first time, and whatever the score is, that will be the score. On the other hand, if you score it second time, like if you attempt the quiz second time, then the average of the scores will be taken. And you should definitely have your written open notes kind of quiz, so you can have your notes available to you the quiz. And you should have paper and pen just in case if there are some calculations to be done, and you should do it on paper and pen. Make sure you have it in front of you as well. Okay, so we were talking about necessary conditions for optimality. The function f of x argument, and the argument x star is equal to the argument of the function f of x. X is in Rn. Now, of course, if I want to be pedantic, I will say x star lies instead of minimum value of the function f of x. But right now, I'm just going to write it as x star equals to, because we are only interested in one of the local minimum of the function f of x. So the statement that we had proven in the previous lecture was, if x star is equal to optimal, if x star is a local minimum of f, classes gradient of f at x star equal to 0. This is known as first order necessary condition. And what we are going to establish today is that the second derivative of the function at x star is a positive matrix, and this is known as second order necessary condition. Again, wanted to remind you, if you are solving problems that are over the space of natural numbers or something, then you cannot satisfy this condition. There is no differentiable possibility. And as an example, if you were scheduling pilots and air hostesses on flights across the US or across the world, then you are basically in a situation where you have a non-differentiable function that you are trying to optimize. But we are not going to talk about those problems here. But people in industrial engineering, ISE department, they kind of solve those problems all the time. If you take some industrial engineering courses, they'll talk about how to solve those kind of problems. In this class, we are looking at differentiable functions only. Okay. So this one, we did the proof in the previous class. I don't want to go over the proof again because it required a lot of writing. But I do want to prove this particular result in this class. I want to prove the second order necessary condition for optimality. And then I'll talk about some implications of this result. Okay. So let's talk about the second second result. So fx star plus d equals to f of x star plus gradient of f of x star transpose d plus half d transpose small o of d square. Yes. This is small o of norm of d square. Okay, so small o, what does small o mean? Write it here. Small o of alpha over alpha, limit alpha goes to 0 is equal to 0. Small o basically contains all the terms that are negligibly small if d is small. I probably want to put an alpha here. Okay, it doesn't matter. I'll let alpha go. Well, let me put alpha here. I'll have alpha here. I'll have alpha here. So I just put an alpha. I put a multiplier, a scalar multiplier alpha around d, and I will pick alpha to be greater than 0, as was the case in the previous class. This is the Taylor series. What do we know about the fact that because x star is a local minimum for any direction d, so for all d in Rn and for alpha sufficiently small, I know that fx star plus alpha d is greater than equal to f of x star because x star is minimum. And I also know that gradient of f at x star is equal to 0, which is the first order necessary condition proved in the previous lecture. So these are the three things we know from lecture 3, lecture 5, which is the previous lecture. No, previous lecture is lecture 4, I think. Yeah, good question. So this becomes small o of alpha square, not norm of d square, because now d could be anything, and the strength, the size of the d is now controlled by alpha. So you can just change it to small o of alpha square. And as I had mentioned, the small o means that as the number here goes to 0, the ratio will go to 0 as well. Any questions so far? So we all agree on these three results that we have studied in the previous lecture. Taylor series from your calculus class. This one from the definition of x star being a local minimum. And this one from first order necessary conditions for optimality that we proved in the previous lecture. So what that gives me is as follows. Zero is less than equal to limit. No, I won't take the limit yet. F of x star plus alpha d minus f of x star over alpha square. And this is equal to. So this term is, remember alpha square is a positive term and this term is greater than equal to 0. So therefore, this entire ratio will be greater than equal to 0. So nothing complicated here. Now I can substitute this particular value, the Taylor series right here, And what I get is, what do I get? I'm taking the difference of these two. This term is equal to 0 because we have proved it. So all I'm left with this term and this term. So this is half d transpose second derivative d plus small o of alpha square over alpha square. And this holds true for all d in Rn and for all alpha greater than 0. What is our favorite thing to do in optimization? Whenever we see alpha on one side of the equation, we just take the limit go to 0. Okay? So let's take the limit alpha goes to 0. Does this term depend on alpha? No. This is the only term that depends on alpha. And what did I say about small o notation? So this ratio will go to 0 as alpha goes to 0. So what I get is limit alpha goes to 0. This term is greater than equal to 0 because of this result. And this holds true for all d in Rn. Okay. Second derivative of a function. Is it a symmetric matrix? Right. So if you go back a few classes earlier, maybe lecture 2 or lecture 3, when we were talking about derivative of functions of multiple variables, we recognize that the second derivative is always a symmetric matrix. So I have a symmetric matrix. I pre-multiplied by d transpose, post-multiplied by d. It's always non-negative, right? So this half doesn't matter. Half is also a positive number, so I can erase that. So I have that d transpose second derivative d. D transpose symmetric matrix d is greater than equal to 0 for all d in Rn. And this matrix is symmetric. What does that imply? That this matrix is positive semi-definite. That's exactly what the second order necessary condition for optimality is. That the second derivative of the function has to be semi-definite, positive semi-definite. So this is the case when you are doing minimization. If you were doing maximization, the first order necessary condition would remain the same. The second order necessary condition would be negative semi-definite. But in this class, we are only concerned with minimization. We are not concerned with maximization. If we were maximizing a function, I'll multiply it by a negative sign, I'll make it a minimum problem. Any questions so far? Okay, so let's look at what the contrapositive statement of these two statements mean. That's the implication of if the first derivative of x bar is not equal to 0, this means x bar is not a local minimum. So if the first derivative doesn't vanish, it's not a local minimum. If the second derivative is not positive definite, positive semi-definite, positive semi-definite, then x bar is not a local minimum. Okay, what does it mean in Python? If you look at the first derivative of the function at x bar, and this looks like 10 raised to minus 15, it's probably a local minimum. But if it is 10 raised to minus 1, then it's probably not a local minimum. If it is 5, it's definitely not a local minimum, no matter what. If you look at the second derivative of the function, you have one eigenvalue which is 5, the second eigenvalue is minus 1. It's not a positive definite, semi-definite matrix, therefore x bar is not a local minimum. If one of the eigenvalues is 5, the second eigenvalue is minus 10 raised to minus 15, it's probably a good candidate for a local minimum. Okay. So just don't go by the sign, because if you use the word sign in MATLAB, even if it is minus 10 raised to minus 15, the sign will be minus 1. Okay, so we cannot really look at the sign. We have to look at the actual value in Python or MATLAB or whatever your favorite language is. No, actually in this class, everyone's favorite language has to be either MATLAB or Python, because we don't accept homework in any other language. But yeah. If you were to work in automotive companies, there are a lot of automotive companies around, and if you are working on optimization problems, most likely you will be using C++, because the ECUs will only take C or C++ as the programming language. So yeah. Any questions so far? So what you see is necessary condition is good for. So this condition is not as important, but the fact that you can certify things or you can rule out possibilities is where necessary conditions shine. What we really want is known as sufficient conditions for optimality, where if something satisfies the sufficient condition for optimality, then it is guaranteed to be a local minimum. So then you actually have a certificate. You can check those conditions, and if those conditions are met, then you know for sure that this is a local minimum of the function f. Okay, so we'll talk about sufficient conditions for optimality. Any questions on this? If not, then I'm going to erase this. Okay. So this is sufficient condition. So x bar is in Rn and it satisfies gradient of fx bar equals to 0, and second derivative is a positive definite matrix. Okay, so I'm not requiring it to be positive semi-definite, but positive definite. And the first derivative is 0, then x bar is a local minimum. Okay, so if I see a point and it has the first derivative 0, the second derivative is positive definite, then I'm guaranteed that it's a local minimum. So I don't have to go through anything else. These are the only two conditions that are required, and these two conditions together is a sufficient condition. So we don't say like, you can of course say first order sufficient condition and second order sufficient condition, but actually sufficient condition requires both these things to be satisfied simultaneously. So let's prove this theorem. Let lambda 1 to lambda n be eigenvalues of second derivative of the function at x bar, and let's say lambda 1 is the smallest one. Okay, so now what should I do? So this term is equal to 0 because the first derivative is 0. What about the second derivative? What are we trying to achieve? What I want to prove is for sufficiently small value of alpha and for any d. So what I want to prove for alpha small for all d in Rn, alpha d is greater than equal to f of x bar, right? This is what I want to prove. So think about how you would go about proving this result. Okay. Okay, so I have this second derivative of the function. Lambda 1 is the smallest eigenvalue of this second derivative matrix. One thing that you can probably recall is if you have D transpose QD and Q is a whatever positive semi-definite matrix, then this is greater than equal to lambda min of Q times norm of D square. We didn't do this in the class, but it's not very difficult to understand why this should be the case. So you have Q minus lambda min Q times identity matrix is a positive semi-definite matrix. So you have a positive definite or positive semi-definite matrix. You pick the minimum eigenvalue of that matrix, multiply it by the identity matrix, subtract that matrix from Q. You still retain a positive semi-definite matrix. Okay, the proof is not too difficult to do. You can do it, but this basically implies this result, because when you do D transpose QD on both the sides, you will realize that D transpose ID is basically norm of D square. And whenever we write norm of D, we are generally referring to the 2 norm, the L2 norm. We are not referring to other norms. When we want to refer to other norms, I'll write it explicitly. So what that implies, statement there implies is that there is something to be done here, okay, in this particular term. So this term is a scalar, it's a small value when alpha is small, but I can do something about this term. So let's look at it. Half. No. Okay, everyone clear why this should be the case? Okay, I just substituted this particular term by the lambda min, which is lambda 1 over 2 of norm of D square plus small o of alpha square over alpha square. So this term is greater than 0. This term is greater than 0 because lambda 1, remember, lambda 1 is the smallest eigenvalue, and lambda 1 is strictly positive because I've assumed that the second derivative is positive definite matrix. So this term is positive, this term is positive, this term is positive. What about this term? Small o of alpha square over alpha square. So remember that small o notation doesn't mean that it has to be positive. Okay, it could be positive, it could be negative. So this term could be positive or negative. This term is definitely positive. But remember that small o means that if I pick alpha sufficiently small, I can make this as small as I want, right? So because this term is going to 0 as alpha goes to 0. So I have a positive number that doesn't depend on alpha, and I'm going to add something that goes to 0 as alpha goes to 0. What that means is by picking an alpha sufficiently small, I can make sure that this whole sum is greater than 0 for small values of alpha, right? As a result of which, this term is going to be greater than 0 for small values of alpha, which is exactly what I wanted to prove. Okay, which is exactly what I wanted to prove. I want to prove that I'm standing at x bar, and no matter what direction I pick, if I take a step in that direction, I want to make sure that the function value must be larger than the function value at x bar. That was my goal. What I proved is slightly stronger. What I proved is actually it's going to be strictly greater than 0. So it's not greater than equal to. This is what I wanted to prove. What I ended up proving was something slightly stronger, that the function value will definitely increase if you take a small step in any direction. This holds true for all D in Rn. Therefore, this holds true for all D in Rn. Now, what I want to ask you is, what if I made this positive semi-definite? how things are going to change in the proof. So if this is positive semi-definite, I could have a value lambda 1 which is equal to 0, because semi-definite matrix means you could have 0 eigenvalues. Positive definite means you cannot have 0 eigenvalue. Eigenvalues always have to be greater than 0. So what happens if lambda 1 was equal to 0? Okay. This term might be 0. This term, there is no guarantee that it's going to be positive or negative, right? So it could be anything. It could be negative as well. Then I cannot make this argument that this thing is going to be greater than 0 for small values of alpha. Okay, so that's exactly the reason why we needed to make this assumption that lambda 1 is strictly greater than 0. So this is called sufficient conditions for optimality. The reason why it's called sufficient condition is because it tells me a set of conditions, if it is satisfied, x bar is guaranteed to be a local minimum. Now the Venn diagram I want you to have in mind whenever you are hearing about necessary condition and sufficient conditions in the context of optimization is as follows. Here is my Rn. Here is my set of points that satisfies necessary condition. Here is the set of points that are optimal. Here are the set of points that satisfies the sufficient conditions for optimality. Right? So you could have optimal points that do not satisfy the sufficient condition. You could have points that satisfy the necessary condition, but they are not optimal. And then, of course, there are points that are outside of these three sets. Okay? So this is what I want you to keep in mind. Just because it is satisfies sufficient condition, well, if it satisfies sufficient condition, it is optimal. You are good to go. But you could have points that don't satisfy sufficient condition and yet they are optimal. So let me give you some examples. Any questions on this proof before we move on? So f1 of x equals to x square, f2 of x equals to x cube, f3 of x equals to x raised to 4. First derivative 2x Okay, so I have these three functions. You don't have to note it down. You can. It's important that you attend to these examples because they are very important. So I have three polynomials: x square, x cube, x raised to 4. Simple and straightforward polynomials. I take the first derivative and I take the second derivative. Let's pick the point x bar equals to 0. Is it the optimal solution for this? Is it the minimizing point of x square? Yes. Is it the minimizing point for x cube? No. X cube goes all the way to minus infinity, so there is no minimum of f2. Does it minimize f3, x raised to 4? It minimizes x raised to 4. Let's look at what the necessary condition and sufficient condition says. Does the first order necessary condition satisfied? In this case, yes. What about second order necessary condition? Satisfied. What about sufficient condition? Satisfied. Right? At x bar equals to 0. So the first derivative is 0, yes. Second derivative is positive, greater than equal to 0, yes. In fact, it is strictly positive, so the sufficient condition is also satisfied. Is the first order necessary condition satisfied here? For this case, so x bar equals to 0, so this is equal to 0, so it's satisfied. Second order necessary condition satisfied? Yes. 6x bar, that's equal to 0. What about sufficient condition? That's not satisfied. Right? What about this third polynomial? First order necessary condition satisfied, second order necessary condition satisfied, sufficient condition not satisfied. Okay? Let's go back to this example. So for x square, the necessary condition, the set of optimal solutions, and sufficient condition, they are the same set, okay, because all those things are satisfied. In the second case, x cube, you have a point that satisfies the necessary condition for optimality, both the first order and the second order, but it's actually not optimal, right? So it's outside of the set of optimal solution. In the third case, you have something that satisfies the first order necessary conditions for optimality and second order necessary condition for optimality. So it lies here, but it doesn't satisfy the sufficient conditions for optimality. Okay? So you can have points here that are not optimal, but satisfies the necessary condition. So just because a point satisfies necessary condition means nothing. Okay? It means really nothing, because you could have a points that satisfy necessary conditions for optimality, but it's neither a minimum nor a maximum. It's just something, just a point in the space. So if you think about it, you could have a function that looks something like this. Or you could have a function. So here at this particular point, your first and second derivatives are equal to 0. Okay? So the necessary conditions would be satisfied, but sufficient conditions are not satisfied. Or you could have a function that looks like this. So at this point, the sufficient conditions are not satisfied, but still it's the optimal point. Okay? So typically whenever you have a flat surface in a function, you will have situations where necessary conditions are satisfied, sufficient conditions are not satisfied, and then you don't know whether you are at an optimal solution or not at an optimal solution. Typically, these kind of situations might come when you are training machine learning models. So you never know whether you are in this situation or this situation. Okay, but if the model does well, you are good to go. If the model doesn't do well, there is no guarantee that you get out of those training algorithms. Okay, any questions so far? No? Okay. There is another sufficient condition that you can use when your function f is convex. So that's where having convex function makes our life easier. So I have a function f from Rn to R. F is convex. Then x star optimal if and only if gradient of f at x star equals to 0. remember, f is convex implies second derivative is positive semi-definite for all x in Rn. So not just at x star, but over the entire space. The second derivative needs to be positive semi-definite. Okay. So if somebody comes in my dreams and tells me that the function that I'm trying to optimize is a convex function, then I have both necessary and sufficient condition which says that the first derivative of the function must vanish at the optimal solution. So it's a very strong result, but then it requires a very strong assumption, which is the fact that the function f is convex. So recall that the second order necessary condition required that the second derivative be positive semi-definite only at the optimal point. That was the second order necessary condition. Now I'm making the assumption that the second derivative is positive semi-definite for all x in Rn. So I'm making a much stronger assumption, not a local assumption at x star, but an assumption over the entire space. And in that case, the first order necessary condition is also sufficient. Now going back to this example, so x raised to 4, if I look at the second derivative at x, it's always non-negative. So 12x square is always greater than or equal to 0. Consequently, wherever the first derivative vanish, which is at 0, you get an optimal point. So in this case, you cannot apply the necessary and sufficient conditions we talked about earlier, but you can apply this particular theorem and establish that x star equals to 0 is an optimal solution. Okay. Any questions on this? Now why should this be the case? Let's look at it. So f is convex if and only if fx plus t equals to, fx star plus t, fx star plus, this has to be greater than or equal to. This was one of the definitions of convex function. If you go back to your notes from lecture 3 or lecture 4, this was one of the definitions of convex function. This term is equal to 0 because of my hypothesis. So if my first derivative vanishes, then that term is 0. And then this implies that f of x star plus d is greater than or equal to f of x star. So the fact that x star is optimal leads to the first derivative vanishing, comes from the first order necessary condition for optimality, so there is nothing to prove there. The fact that the first derivative vanishes, then x star is optimal, comes from this very elementary statement. We don't even have to go through any limits or any complicated stuff. Just use the definition of convexity and we get the answer. Right? So what we have done so far is we have understood the necessary conditions for optimality, sufficient conditions for optimality, and the case of convex function, both necessary and sufficient conditions for optimality. Now let's get to the algorithm design. So now that we know about these two facts, necessary and sufficient conditions, how do we design an algorithm that no matter where I start from, so if I am standing at x naught in the beginning and I need to figure out where x star is and all I have is a function, how do I figure out where to move, okay, which direction to go to in order to get to the optimal solution? So I'm standing here at x naught, here is my x star, and I have a program or I have a function call where I can query the value of the function f of x and the first derivative of the function and the second derivative of the function. So I created three different, so I have a function, somebody gave me the function, and I created three different modules. One that computes the function value, second that takes as input x, computes the first derivative, and another one that takes the input x and computes the second derivative. Now the problem that we are faced with is I'm standing at x naught, I have so many directions to pick. How do I know which one is the right direction? Which direction I should be taking a step in so that I get closer to x star. Okay, eventually I want to get to x star. So that's the goal of algorithm design. Any thoughts? How should we proceed? What should we do? Let me write it mathematically. I'm standing at x naught. I want to get to a direction d so that f of x naught plus d is closer to fx star. Okay, maybe that's not very well crafted statement. So I need to craft it in a slightly better fashion. So how about I write it as f of x naught plus d is less than f of x naught. So find d such that f of x naught plus d, like ideally I want f of x naught plus d is closer to f of x star, that's what I want. I really don't know how to write it mathematically. So let me write it mathematically as f of x naught plus d is strictly less than f of x naught. So I'm standing at x naught, I've picked this point randomly, so I'm pretty sure that I'm not at the optimal solution, so I'm not at x star, and now I need to pick a direction d so that my function value is lower. Okay, that's the simple and straightforward mathematical problem I want to solve. So let's think about it. Let's do a Taylor series expansion of f of x naught plus d. It is f of x naught plus gradient of f of x naught transpose d plus small o of d. How should I pick d so that this term is less than f of x naught? Any thoughts? If you were in this situation in 1600, whatever, 50 or something, what would you do? There is no field of optimization at that point of time. People were trading tulip bulbs, and the first stock market crash happened in that era, in that age, and you were faced with this problem. So Newton sent you a letter and said, you know, I'm trying to solve this problem, I don't know what to do. What would you do? How would you pick the direction d in which to descend? Okay, so what do I know at x naught? So I have this this Python script that tells me the value at x naught, the first derivative at x naught, and the second derivative at x naught. So it computes and gives it back to me. How about this? I pick d to be negative gradient of fx naught. Okay, so then what happens? F of x naught plus d becomes f of x naught minus Okay, so there is some improvement here. So my first derivative would not have vanished because x naught was not an optimal solution. So this is definitely non-zero. If this is non-zero, then the norm square is also going to be non-zero. I have here a negative sign, so this must be negative value. So I have at fx naught, I was standing at fx naught. I'm subtracting a negative value from it. So I'm definitely getting to a point where I'm descending. The value of the function is reducing. But now I have this annoying term O of norm of D. Okay, and I need to do something about it. How would you fix that problem? This O of D could be large, could be small, right? How can I fix this problem? Yes?
Isn't that D also negative gradient of f to xo? So could you just plug that into the other D as well?
Yeah, so this D is this D, right? So this gradient could be very large. So this number could be pretty large, right? So I want to be able to control this particular number. I still want to have this quality, which is the function value is reducing, but I want to make sure that I control this particular term. What's the way to control the small o terms? Yes?
We introduce alpha to make it.
Yeah, so we pick a small step size. So alpha, we pick an alpha multiplied by the gradient. So I have this alpha here, and then I have a small o of alpha. So by picking alpha sufficiently small, I can make this very close to 0. But this term would still be negative. Okay, so alpha is strictly positive. So alpha is greater than 0, but small. Now it's plausible that by picking an appropriate value of alpha, so I have picked a value of D, but by picking an appropriate value of alpha, I can make sure that I get to a point x naught plus D or alpha D, x naught plus alpha D, which is strictly less than f of x naught. So I've identified a direction. I have identified that a small step size needs to be taken in order to get to a point which has a lower value than the original point. And then I can do this all over again. I can pick the next direction D to be minus alpha of gradient of f of x1, and then minus alpha of gradient of f of x2, and so on and so forth. Okay, and that's our gradient descent algorithm. Okay, so gradient descent, what does descent mean? At every point of time, the function value is going to reduce from where I am standing at this point of time. So that's the descent part, and the gradient comes from this term here. So the descent direction is actually coming out of the gradient of the function evaluated at x naught or xk. Okay, I think we are out of time. So we have talked about gradient descent algorithm. Now we'll build upon this background in the next class, and we'll talk about a whole bunch of gradient descent algorithms that are used for solving problems of this type. So thank you, and see you on Wednesday.